Between 1943 and 1945, Allied intelligence services carried out unprecedented operations to identify, assess, and neutralize German technological developments that challenged conventional military capabilities. More than 1,500 industrial facilities were catalogued as priority targets for strategic bombing, not for their immediate productive capacity, but for the experimental projects they housed. The Wunderwaffen represented the last attempt of the Reich to reverse a lost war through science applied to destruction. These programs ranged from intercontinental aircraft to chemical weapons capable of annihilating entire cities, including guided missiles and artillery guns that challenged the known laws of physics. What specific technologies caused the greatest concern in Washington and London? To what extent were they close to altering the outcome of the war? Why did the Allied race to capture German scientists after 1945 become a maximum strategic priority? The obsession of the Reich, the birth of the Wunderwaffen. The surrender of the 6th German Army in Stalingrad on the 2nd of February 1943 represented a strategic turning point from which the Third Reich would not recover. During 5 months of sustained urban combat under temperatures that reached 40 degrees below zero, the Soviet encirclement had nullified the operational capacity of forces initially composed of more than 280,000 soldiers. The combination of attrition, lack of supplies, and the inability to receive reinforcements led to a total collapse. Nearly 146,000 men died before the capitulation, 91,000 were taken prisoner, and only a minimal fraction would return to Germany in the following years. The material impact was equally profound. The accumulated losses of Germans and their allies on the Eastern Front since mid-1942 exceeded 1 million soldiers, a figure that permanently weakened the offensive capacity of the Reich. The promotion of Friedrich Paulus to Field Marshal on the 30th of January, accompanied by the explicit expectation that he would not surrender, evidenced the distance between political orders and the real situation on the ground. With his decision to capitulate, a Prussian precedent was broken, and it was confirmed that Germany was facing a scenario that surpassed any previous military tradition. The military deterioration was not limited to the east. In North Africa, the defeat at El Alamein in November of 1942 had initiated a retreat that would culminate with the surrender of about 250,000 Axis troops in May of 1943 in Tunisia. At the same time, Allied bombings on German cities were increasing in intensity and frequency. The operation against Hamburg in July of 1943 caused massive fires that destroyed large urban areas and paralyzed industrial nodes. Waves of Allied bombers repeatedly struck critical facilities, including ball-bearing production in Schweinfurt, whose vulnerability was demonstrated in the attacks of August and October. German industrial capacity, despite reorganization efforts, remained behind the combined production of its adversaries. In 1943, the United States produced nearly 96,000 planes, compared to about 8,000 German aircraft. Tank production showed an even greater gap, with the Soviet Union and the United States manufacturing more than double the armored vehicles than the Reich. The war was progressively transforming into a conflict of resources and production, a field in which Germany had no advantage whatsoever. In this context, the Ministry of Propaganda, under the leadership of Joseph Goebbels, intensified its intervention to sustain the internal cohesion of the country. On the 18th of February 1943, at the Berlin Sports Palace, Goebbels presented the need to mobilize all material and human resources of the Reich. The speech, carefully prepared and directed at a selected audience, also introduced an element aimed at projecting confidence towards the immediate future. The insinuation that Germany possessed or was developing advanced technologies capable of altering the course of the war. The term Wunderwaffen began to appear recurrently in official propaganda as a reference to supposedly revolutionary weapon systems. The idea was not entirely new, but since the defeat at Stalingrad, it acquired a structural function, to maintain the expectation that German technological superiority could still provide a strategic opportunity. The use of the concept addressed several needs. On one hand, it aimed to sustain the morale of the civilian population through the notion that the Reich maintained an exceptional scientific capacity. On the other, it sought to reinforce confidence among the troops, who were already facing a succession of withdrawals. Finally, it aimed to influence the strategic calculation of the Allies, who had to consider the possibility that Germany might develop unprecedented weapons systems. The design of this narrative was based on widely used propaganda principles, repeating simple messages, avoiding verifiable details that could be refuted, and projecting an image of technological strength even in a context of military setbacks. Deliberately presented ambiguously, the Wunderwaffen offered a promise without committing to concrete results. Adolf Hitler's personal conviction regarding German engineering decisively contributed to the expansion of the concept. For the Führer, the country's scientific history, dominant in Europe before 1914, served as a foundation for believing that German technical superiority was capable of generating solutions able to overcome the overwhelming industrial power of the Allies. The ideological interpretation of this legacy led him to consider it inevitable that Germany could develop weaponry of an unprecedented technological level. This vision fueled direct interventions in the development of projects, even when lacking adequate technical training. Hitler's decisions repeatedly altered the course of advanced programs, generating delays and tactical deviations. The case of the Messerschmitt Me 262 jet fighter became a paradigmatic example. Presented as an interceptor in 1943, Hitler ordered it to be converted into a fast bomber, a modification that involved structural redesigns and significant delays. By the time it entered service as a fighter, the Luftwaffe had already lost much of its air defense capability. The Reich's industrial system exhibited a remarkable concentration of technical knowledge, with companies such as Krupp, Junkers, Heinkel, IG Farben, or Messerschmitt accumulating decades of experience. However, they operated within a highly fragmented administrative framework. Different agencies simultaneously competed for limited resources, which led to duplication of projects, lack of coordination, and constant difficulties in establishing strategic priorities. The rivalry among the Ministry of Armaments, led by Albert Speer, Hermann Göring's Luftwaffe, and the SS, which from 1944 incorporated secret projects under the command of Hans Kammler, exacerbated these dysfunctions. In the absence of a unified planning structure, the proliferation of advanced technological initiatives multiplied even as the availability of raw materials and specialized labor rapidly diminished. Since 1943, the Reich increasingly relied on forced labor and the employment of prisoners in the armaments industry. Production conditions were extremely demanding and further deteriorated overall efficiency. In underground facilities like Mittelwerk, intended for the production of the V-2 rocket, the combination of fatigue, food shortages, and work overload reduced productivity and caused systematic failures in components. German reports indicated that sabotage was frequent and affected significant percentages of ammunition and machined parts. This phenomenon contradicted the official narrative about supposed German precision and directly impacted programs that required very tight technical tolerances. The Allied bombings forced Germany to move numerous factories to underground facilities, mines, railway tunnels, and specifically excavated complexes. Although this dispersion partially protected production, it created a logistical complexity increasingly difficult to manage. The need to transport components between multiple centers slowed down processes and increased vulnerability to air attacks. The scarcity of strategic materials like tungsten, molybdenum, and synthetic rubber forced continuous modifications in designs, which added new delays. The supply chains became unable to sustain the simultaneous development of technologically ambitious programs. Within this environment, the Nazi leadership opted for a strategy that sought to compensate for industrial inferiority through high-impact innovations. The proliferation of advanced projects concentrated on various priority areas. In the aeronautical field, research focused on jet fighters, rocket interceptors, flying wing platforms with low radar signature, and bombers capable of operating at long distances. In missile matters, radio-guided bombs, air-to-air missiles, and the V-1 and V-2 rockets, which represented the first ballistic systems used in combat, were developed. Long-range artillery included both expanded conventional designs and large-scale experimental projects. In parallel, progress was made in the development of chemical and nerve agents such as tabun, sarin, and soman. The nuclear program, known as Uran Project, suffered internal fragmentation, lack of resources, and conceptual errors that limited its progress, in addition to Allied sabotage actions. The logic underpinning these projects was based on the premise that a qualitative advantage could counteract Allied quantitative superiority. In theory, a higher speed fighter, a guided missile, or a long-range experimental platform could produce disproportionate effects. However, the development and mass production of the new generation weaponry required a stable industrial environment and a continuous availability of resources, conditions absent in Germany after 1943. Each project absorbed specialized materials, complex facilities, and technical staff that were already scarce. The result was a proliferation of prototypes without most reaching the large-scale production phase. The investment in Wunderwaffen thus became a characteristic element of the late Reich, an effort to achieve decisive solutions in an environment where logistical breakdown, military pressure, and industrial crisis limited any real possibility of success, while the conflict moved towards a phase in which these innovations, even if completed, would hardly have significantly altered the overall development of the war. The sky in ruins, the extreme challenge of the impossible aviation. By the summer of 1944, the airspace of the Reich had become a territory over which the Luftwaffe could hardly hope to exert partial control. Every day, formations of American bombers, composed of hundreds of B-17 and B-24, crossed the English Channel, escorted by long-range P-51 fighters capable of accompanying them throughout the entire journey. The altitude and pace of these attacks imposed constant pressure on the German defense. While the daytime bombers concentrated their attacks on industrial complexes, refineries, and railway networks, the RAF maintained the nighttime offensive with its Lancaster and Halifax, whose load capacity and systematic use of incendiaries allowed for the destruction of entire urban areas. The Luftwaffe had lost the offensive initiative and operated with limited resources, a scarcity of fuel, pilots in accelerated training, and an insufficient number of fighters capable of matching the performance of the Allied models. The standard defense planes, primarily the Messerschmitt Bf 109 and the Focke-Wulf FW 190, faced cumulative disadvantages. Their engines required a high fuel consumption during the climbs necessary to intercept formations, flying at altitudes above 8,000 meters. Their pilots, with fewer hours of training than the Americans and British, performed brief interceptions before having to descend due to lack of fuel. In an aerial conflict increasingly determined by autonomy, speed, and mechanical endurance, these structural limitations progressively reduced the German response capability. To compensate for this situation, the Ministry of Air explored alternatives that did not replicate the parameters of conventional aviation, but offered quick solutions through simple and economical systems aimed at defending specific targets. From that need emerged the concept of the emergency interceptor, a type of aircraft designed to reach operational altitude in a short interval, carry out a single attack, and end the flight through partial recovery procedures or unconventional landing. The most extreme project in this category was the Bachem-Ba 349 Natter. Designed in 1944, the Natter represented a radical approach focused on industrial simplicity and climb rate through rocket propulsion. Its main structure used plywood and welded steel tubes, a set that could be assembled in approximately 1,000 hours by unskilled workers. The aircraft measured about 6 meters in length and lacked complex aerodynamic surfaces, which allowed the manufacturing process to remain within minimal parameters of time and materials. The propulsion system combined a Walter liquid-fueled rocket engine with 4 Schmidding solid boosters. The main engine produced around 1,700 kilograms of thrust through a highly reactive mixture of concentrated hydrogen peroxide and nitrogen compounds, whose handling required strict precautions due to the risks of corrosion and spontaneous combustion. The auxiliary rockets provided initial thrust during the first few seconds of vertical launch, at which point the Natter remained guided by a 24-meter tower that guaranteed initial stability. After the solid rockets were exhausted, they detached automatically, and the aircraft continued its ascent, powered solely by the Walter engine. In ideal conditions, it could reach about 12,000 meters in approximately 80 seconds. The armament consisted of a battery of unguided rockets mounted in the front section. The planned attack was based on an ascent controlled by radio command from the ground. Once inside the operation zone, the pilot took control, selected the target within the bomber formation, and fired the entire load in a single launch. The separation of the front section, equipped with parachutes to recover the pilot, was part of the final protocol. The main rocket engine, due to its strategic value and technical complexity, had its own recovery system. The remaining airframe was considered expendable. The first unmanned tests were conducted at the beginning of 1945, but the first manned launch ended in an accident a few seconds after takeoff, without being able to determine the cause with certainty. Despite this setback, several units reached the deployment phase in the last months of the war, although none operated in actual combat. While the Natter represented the most direct route to a single-use interceptor, another group of designers sought to reduce German vulnerability through advanced aerodynamic configurations. Among them were the Horten brothers, pioneers in the flying wing concept. Their approach eliminated the conventional fuselage to reduce aerodynamic drag and maximize efficiency. This approach gained relevance when Hermann Göring issued the specification for the so-called 1,000 by 1,000 by 1,000. A bomber capable of carrying 1,000 kilograms of bombs over 1,000 kilometers at a speed of 1,000 kilometers per hour. No traditional German design could simultaneously meet these requirements, but the drag reduction offered by the flying wing opened up a theoretical possibility. The result was the Horten Ho 229, an aircraft with a wingspan close to 16 meters and powered by 2 Junkers Jumo 004B turbojets. Its structure combined steel in the central section and plywood in the wings, used both due to the scarcity of light metals and for ease of manufacturing. The Horten brothers added an innovative element for radar signature reduction. They mixed conductive charcoal powder with resins and paints, creating a material capable of absorbing part of the electromagnetic energy emitted by Allied radars. Added to the absence of prominent vertical surfaces, the design exhibited a reduced radar signature compared to conventional aircraft of the time. The first prototype flew as a glider at the beginning of 1944. The second one, equipped with engines, reached speeds exceeding 800 kilometers per hour during tests conducted at the end of that year. A failure in one of the engines caused the loss of the aircraft during a test flight in February of 1945, which did not prevent the authorities from ordering the continuation of the development. A third prototype was in the final assembly phase when American troops captured the facility. The aircraft was taken to the United States for study. Decades later, tests conducted with a replica confirmed that the design possessed low detectability features comparable with principles used in modern stealth aircraft. Beyond the interceptors and aerodynamic experiments, the Luftwaffe explored the possibility of developing an intercontinental bomber capable of reaching United States territory. This program, known as the America Bomber, emerged in 1938 and gained relevance after the United States entered the war. The aim was to have an aircraft capable of covering a distance of over 11,000 kilometers on a round trip with a significant bomb load. Various manufacturers submitted proposals. Messerschmitt developed the Me 264, a 4-engine aircraft that introduced solutions such as tanks integrated into the wings to increase range. Junkers proposed the Ju 390, an extension of its strategic transport, Ju 290. Focke-Wulf developed the Tar 400, while the Horten brothers suggested a large flying wing equipped with 6 jet engines. Although prototypes of the Me 264 and the Ju 390 were built, the progression of the program was affected by structural factors. The intensification of the Allied bombings repeatedly interrupted the supply of materials and manufacturing processes. The availability of aviation fuel decreased drastically following the loss of synthetic production facilities. Additionally, the High Command considered that a small number of long-range attacks would not provide decisive strategic advantages and instead would provoke an immediate increase in reprisals. The decision to cancel most of the initiatives was formalized in 1944, and the program was abandoned. Allied research on these developments revealed the variety of technological initiatives that Germany had attempted to implement to balance its material inferiority. Information from aerial reconnaissance, captured remains, and pilot statements allowed identification of early-stage projects that never managed to operate significantly. The Allied assessment concluded that, although some designs had notable advances, the industrial and logistical conditions of the late Reich prevented them from reaching a scale that could alter the overall military situation. The Luftwaffe, weakened by the lack of fuel, the loss of experienced pilots, and the relentless pressure of Allied strategic bombing, failed to incorporate these innovations with the necessary speed. By the time the most promising prototypes demonstrated their technical viability, German industrial infrastructure was too deteriorated to sustain their mass production. In the final months of the conflict, the skies over Germany remained dominated by Allied aviation, while the advanced projects remained in various states of development without fulfilling the decisive role their designers had projected, thus entering a stage of urgent experimentation that would shape the course of the air programs that would emerge in the following months. Hidden impact, the silent insurgency of guided missiles. Until 1943, the use of aerial and naval weaponry was governed by ballistic principles that had remained practically unchanged since the beginning of the 20th century. Bombs followed paths determined by gravity. Artillery projectiles relied on prior calculations established through firing tables, and torpedoes navigated following straight courses at known speeds. Consequently, the success of any attack depended on direct approach to the target, which exposed the aircraft to anti-aircraft defenses and compelled ships to endure salvos with a high margin of dispersion. The Luftwaffe had observed for years the inherent limitations of this method. The experience accumulated since the Spanish Civil War showed that a ship maneuvering at 30 knots could move away tens of meters during the fall of a bomb dropped from several thousand meters high, drastically reducing the likelihood of impact. Even dive bombers, capable of achieving greater precision, had to get so close to their targets that they were exposed to the concentrated fire of naval guns and anti-aircraft batteries. The development of a system that allowed the trajectory of a projectile to be modified during its descent represented a structural change in the conduct of combat. The starting point of this advance came from Max Kramer's experiments at the German Aeronautical Research Institute. Kramer explored the possibility of coupling radio-operated control surfaces to existing bombs, allowing the operator in the aircraft to maintain manual correction of the course. His proposal was realized in the Fritz X, a guided modification of the PC-1400 armor-piercing bomb. This projectile, with an approximate length of 3 meters and a total weight of more than 1,300 kilograms, retained its original penetrating capability, sufficient to penetrate armored decks of considerable thickness. The guidance system, mounted in the rear section, incorporated a radio receiver and servo motors that acted on movable surfaces. To facilitate the operator's observation, flares were added that generated a trail visible from several kilometers away. The launching aircraft, generally a Dornier Du 217, maintained stable heading and speed while a second crew member used a directional control to keep the projectile visually aligned with the target. This technique, known as MCLOS, required simultaneously observing the target and the bomb's trail, keeping both within the same visual axis. The initial tests conducted in test fields demonstrated that the system could achieve unprecedented accuracy compared to any unguided bomb. From altitudes above 8,000 meters, the recorded impacts were concentrated in a relatively small area, making its use against warships maneuvering at speed viable. The operational debut of the Fritz X took place in September of 1943, when the Italian fleet was sailing towards Allied ports to surrender after the fall of Mussolini. A German bomber launched 2 projectiles against the battleship Roma. The second impact hit internal storage and generated an explosion that sank the ship in a few minutes. In subsequent days, several Allied ships were damaged or sunk by similar attacks. The Allied reaction was immediate. Electronic countermeasures were implemented to interfere with the guidance signals, and anti-aircraft defense was reorganized to prevent German bombers from maintaining the constant course needed to control the projectile. By mid-1944, the increase in Allied air superiority and the systematic use of frequency jammers progressively limited the effectiveness of the Fritz X, although its impact on the subsequent development of guided weapons was significant. While the Fritz X was conceived as a precision anti-ship weapon, another project aimed to solve a different challenge: the need to attack compact formations of Allied bombers without approaching the range of their defenses. German fighters attempting to get close to the formations of B-17 and B-24 had to pass through a volume of defensive fire generated by dozens of heavy-caliber machine guns coordinated to cover all angles. The development of the Ruhr-style X-4 missile was specifically oriented to provide a solution to this problem. Unlike the Fritz X, the X-4 was an air-to-air missile that incorporated self-propulsion through a rocket engine and used a wire-guided system. Approximately 2 meters in length and about 60 kilograms in weight, the missile incorporated stabilizing fins and movable surfaces controlled by signals sent from the launching plane through wires that unrolled during the flight. The use of cables instead of radio had several advantages. It eliminated the possibility of enemy electronic interference and guaranteed a stable connection between the pilot and the missile. The rocket engine, based on hypergolic fuels, propelled the X-4 to speeds close to 900 kilometers per hour, allowing it to intercept bombers from safe distances. Its warhead, equipped with an acoustic proximity fuse, detonated upon detecting changes in sound frequency produced by the target bomber's engines. However, operating the system presented practical difficulties. It required the pilot to maintain visual alignment with the missile and the target while maneuvering his own aircraft, a complex task in actual combat. For this reason, its use was considered primarily on 2-seater platforms, where a dedicated operator controlled the guidance. Although numerous X-4 airframes were manufactured, the destruction of the facilities that produced its engines prevented the system from entering regular service. Even so, the concept directly influenced wire-guided anti-tank missiles developed at the end of the war. Another German initiative sought to fuse a manned aircraft with a large explosive payload to create a weapon capable of destroying heavily protected structures. The Mistral system consisted of a fighter plane mounted on a modified bomber, whose front section housed a warhead designed to pierce concrete and steel before detonating. The pilot took off controlling the unified combination. Near the target, the autopilot of the lower aircraft was activated and separated, allowing the explosive-laden aircraft to continue its straight path to impact. Various variants of the Mistral were evaluated to attack bridges, industrial plants, and other strategic targets, especially during the final months of the war. Although technically feasible, the project did not reach a broad operational deployment due to the deteriorating military situation of the Reich and the shortage of pilots with sufficient experience to execute it. In parallel to these guided weapons controlled by human operators, Germany also developed long-range autonomous systems. The V-1, designed as a primitive cruise missile, used a pulse jet engine as its power plant and a gyro-based autopilot to maintain preset course and altitude. Although its accuracy was limited, it allowed targets to be attacked at tens of kilometers, with minimal active participation from the operator. The V-2, on the other hand, represented the first operational use of a liquid-fueled ballistic missile. Its engine provided thrust that carried it to altitudes over 80 kilometers before beginning a descent in a ballistic trajectory towards its target. The guidance system, based on gyroscopes and mechanisms that adjusted the thrust during the ascent phase, reduced deviations but did not achieve accuracy comparable with later systems. Both projects demonstrated that it was possible to combine autonomous propulsion and internal guidance to attack targets located at distances that far exceeded the capabilities of conventional artillery. The Allied reaction to the appearance of these weapons was immediate and meticulous. Units were established to evaluate each type of guided projectile, identify electronic signals associated with the control systems, and design methods to neutralize them. The interference of the Fritz X signals through specific devices progressively reduced its effectiveness. The capture of specimens of the X-4 and other prototypes allowed intelligence services to reconstruct their guidance principles and foresee their possible evolution. Technical reports prepared in 1944 and 1945 detailed diagrams, materials used, and internal control logics, laying the groundwork for more advanced countermeasures that would be developed in the following decades. The psychological impact that these weapons had on Allied crews was significant. Systems capable of altering their trajectory mid-flight represented a different threat from any conventional projectile. Technical accounts of the time describe how observers on board ships or planes could distinguish the trail of the guided projectile, adjusting its course as it approached the target, forcing evasive maneuvers that would previously have been unnecessary. Although their operational deployment was limited by production problems and the progressive deterioration of the German industrial apparatus, the projects demonstrated that it was possible to direct weapons towards a target with a degree of precision superior to that of traditional artillery or aviation. By the end of the war, German laboratories had generated a variety of guided systems ranging from anti-ship bombs to air-to-air missiles and long-range ballistic weapons. Many of them did not reach mass production, but they established technological principles that would directly influence later developments. Subsequent Allied research confirmed that most of these projects were in transitional phases between prototype and limited production, without any real capacity to decisively alter the military situation. Still, the conceptual advance had been achieved. The possibility of correcting the trajectory of a projectile after its launch would become an essential feature of modern weaponry. In the context of the late Reich, these guided weapons emerged as a direct response to the strategic imbalance and marked a shift in the technological conception of combat, paving the way for innovations that would continue to evolve in the following months as the war moved towards its final phase. Titanic weapon, the shot intended to cross continents. The use of artillery as a long-range strategic instrument had precedence before the Second World War, but it was in the context of the late Reich that this idea was transformed into a central component of the German technological pursuit. During the First World War, the so-called Paris gun had demonstrated that it was possible to bombard a city located more than 100 kilometers away with a projectile fired at speeds sufficient to reach the stratosphere. Although the material impact of this weapon had been limited, its psychological effect was significant. The lessons derived from that experience directly influenced the military thinking of the Third Reich. In a global conflict where Allied industrial superiority far exceeded the German, the possibility of attacking large cities without exposing aircraft or troops represented an attractive alternative. Projectiles launched from remote positions could, in theory, compensate for numerical imbalances by creating a constant risk for enemy urban centers. This logic drove a series of projects aimed at increasing the range of artillery beyond conventional limits. The underground installation at Mimoyekes, built in northern France, became the most representative example of this ambition. In 1943, Hitler authorized the creation of a complex dug deeply into limestone hills in Pas-de-Calais, at a distance that allowed reaching London with extreme range artillery. The choice of location responded to the geological stability necessary to withstand the recoil and vibrations generated by a battery of unusually dimensioned cannons. The project, designated V3, was based on a technical principle distinct from conventional artillery. Instead of using a single propellant charge, the cannons incorporated a series of side chambers located along the main tube. Each chamber detonated in sequence as the projectile advanced, maintaining constant pressure and progressively increasing firing velocity. This multiple charge system, used for the first time in a large-scale weapon, aimed to launch projectiles of approximately 140 kilograms to distances exceeding 150 kilometers. The construction of the complex required the excavation of tunnels, galleries, and incline shafts with an intensity that reflected the priority assigned to the project. Thousands of German workers and Soviet prisoners of war participated in the process. The design included 2 sets of shafts, each comprised of several pieces arranged at an angle to reduce exposure to enemy fire and channel structural forces towards the rock. An internal railway system, connected to the main line between Calais and Boulogne-sur-Mer, transported ammunition and materials. The depth of the galleries allowed for the storage of shells and avoided direct detection through aerial observation. Although the Allied authorities initially did not know the exact function of the site, reconnaissance flights identified significant construction activity. Photographs showing camouflaged entrances and anomalous rail displacements aroused suspicion. By the end of 1943, Allied bombings began systematically. The development of large penetration bombs, such as the Tallboy of more than 5 tons used by the RAF, allowed for attacks on the interior of the complex despite its depth. The detonations collapsed tunnels, cut railway lines, and destroyed critical sections of the inclined shafts. The combination of structural damage and construction delays led German authorities to suspend the project in July of 1944. When Allied ground forces took the facility in September, they found the infrastructure partially destroyed and incapable of operating. Only after a thorough examination of the site was it understood that the system was intended to operate as a continental-range artillery weapon. The potential impact of the V3 led British officials to consider the facility as a strategic threat that needed to be permanently neutralized. While the V3 was being developed in French territory, another project of enormous proportions was already underway on the Eastern Front. The Schwerer Gustav, built by Krupp, represented the largest railway cannon ever operational. Its caliber, of 800 mm, allowed it to fire shells weighing several tons. The piece, mounted on 2 parallel tracks, required specific infrastructure for its transport and assembly. Each move involved the arrival of dozens of rail cars carrying components, cranes, auxiliary material, and technical personnel. The coordination of thousands of workers and specialists was necessary to assemble the structure and prepare the firing position. The design of the Gustav had been conceived to destroy reinforced concrete fortifications, underground depots, and coastal batteries, targets that conventional artillery or aviation could hardly neutralize without a considerable increase in resources. The weapon was used for the first time during the siege of Sebastopol in 1942. To position the cannon, it was necessary to lay an additional railway line of more than 15 kilometers, level the land, and build trenches where the piece would be protected between shots. Once ready, the Gustav launched several dozen shells against Soviet fortifications. Although some targets were hit, the overall contribution of the weapon was relatively limited due to the long interval between shots and the complex logistics associated with each operation. After the end of the siege, the cannon was taken back to Germany for maintenance and replacement of the main barrel. Its possible deployment against Leningrad was cancelled when the German lines began to retreat in the face of Soviet counteroffensives. The Gustav did not participate in combat again and was destroyed by the German troops themselves to prevent its capture. Its twin weapon, Dora, also did not achieve effective use before being found by United States forces in 1945. The railway superguns demonstrated several structural limitations. Their size made them difficult to conceal. They were completely dependent on railways, which made them vulnerable targets for enemy aviation. Their rate of fire was low, and their maintenance required a disproportionate amount of materials and personnel compared to the actual military effect they could achieve. However, their development reflected the German High Command's belief that extraordinary weapons could alter strategic dynamics through psychological impact and pinpoint destructive capability on selected targets. In parallel with these terrestrial developments, proposals emerged that aimed to extend the range of artillery beyond atmospheric limits. The project known as Sonnengewehr was the most extreme example of this trend. Based on astronomical ideas and conceptual principles associated with Hermann Oberth, the project contemplated the construction of an orbital station equipped with a parabolic mirror capable of concentrating solar radiation on a specific point on the Earth's surface. The intention was to produce enough heat to destroy structures or set large areas on fire. The theoretical design included mechanisms to precisely orient the mirror, electrical generation systems based on solar radiation, and habitable modules with autonomous life support. The station would have been assembled in space using successive rocket launches derived from the V2, each carrying prefabricated sections. The technical analysis of the concept quickly revealed its limitations. The total mass of the structure exceeded any known launch capacity. The precise alignment required to concentrate solar energy was unfeasible with the mechanical systems available at the time. The construction of the mirror itself posed insurmountable problems, as a surface of those dimensions required tolerances impossible to achieve with existing materials. Thermal dispersion, radiation degradation, and the difficulty of maintaining stable orbital control made the project a purely conceptual construction. The documents captured in 1945 and analyzed by Allied engineers confirmed that the complete development of the Sonnengewehr would have required decades of technological advances. The set of superweapons developed by the Reich in this category reflected a recurring trend of the final stage of the conflict, prioritizing extraordinary solutions instead of gradual increases in conventional weaponry. The V3 never reached operability. The railway superguns could only be employed in exceptional circumstances and with limited results. The Sonnengewehr remained in the theoretical realm. Even so, the Allies dedicated considerable resources to neutralize or study these projects. The intensive bombings on Mimoyekis and the capture of components of the Schwerer Gustav showed the attention that the Allied commanders gave to any weapon capable of operating beyond the traditional range. Despite their limited influence on the overall outcome of the war, these developments introduced concepts that found continuity in later decades. The multi-stage propulsion applied to the V3, the structural analysis of large-caliber weapons, and the first studies on orbital installations were precedents that influenced post-war research programs. Various German scientists, transferred to the United States and the Soviet Union, later contributed to advances in ballistic missiles, rocketry, and space systems. In this context, the Reich's obsession with extending the range of its weapons beyond any previously established limit reflected both the strategic desperation of its final years and the beginning of technological ideas that would continue to evolve in the subsequent months of the conflict. Forbidden science, the deadly threshold of the Reich's laboratory. In 1936, during routine investigations on insecticides in the laboratories of I.G. Farben, the chemist Gerhard Schrader synthesized a compound that forever changed the German understanding of chemical warfare. The substance, obtained while attempting to improve the effectiveness of organophosphate pesticides, immediately caused severe symptoms in Schrader himself and his assistant: extreme constriction of the pupils, breathing difficulties, and temporary loss of muscle control. The reaction indicated that it was not a simple insecticide, but an agent capable of directly affecting the nervous system. The military classification came immediately. The compound was named tabun and became the first agent of a family of substances that, due to their lethality, marked a technical rupture from the gases used during the First World War. The operation of these nerve agents was based on a precise physiological mechanism. The compounds inhibited the action of acetylcholinesterase, an enzyme responsible for deactivating acetylcholine in nerve junctions. With this function nullified, acetylcholine accumulated, producing the continuous transmission of impulses that made muscle relaxation impossible. The glands began to secrete fluids uncontrollably, the respiratory muscles became progressively paralyzed, and brain activity was altered until it caused seizures. The sequence of symptoms, acute miosis, bronchoconstriction, excessive salivation, vomiting, tremors, and paralysis, could progress to cardiopulmonary collapse in a few minutes if the dose was high. The relative potency of these compounds far exceeded that of the agents used 2 decades earlier, and turned chemical weapons into an instrument that could cause immediate immobilization over a wide dispersion radius. The discovery stimulated a secret program. In 1937, the Ministry of War prohibited the publication of Schrader's patent and ordered the start of industrial production of tabun. In the following years, IG Farben built facilities dedicated to the manufacture of nerve agents on a massive scale, the most important of which was located in Dyhernfurth in present-day Poland. The industrial complex used forced labor from a nearby camp and was designed to maintain a continuous production of thousands of tons annually. The process required the handling of extremely reactive substances and posed permanent risks to the workers. By 1942, Germany had already accumulated a considerable amount of tabun and had modified artillery shells, aerial bombs, and rockets for its use. Scientific research did not stop with tabun. In 1938, Schrader synthesized an even more toxic compound, which was named sarin. Studies showed that its potency was several times higher and that it required significantly smaller doses to cause rapid death. Industrial production began in 1943 after resolving difficulties related to the stability of the chemical precursors. A second factory, in Falkenhagen, complemented the Dyhernfurth effort. Germany produced between hundreds of kilograms and several tons of sarin, according to later estimates. Although the arsenal was smaller than that of tabun, the lethality of the compound made it a central element of German chemical planning during the final years of the war. A third agent, soman, was synthesized in 1944 under the direction of the chemist Richard Kuhn at the Kaiser Wilhelm Institute. Its toxicity exceeded that of the previous compounds and presented characteristics that complicated decontamination efforts. Unlike sarin, its low vapor pressure kept it active for extended periods. Its industrial production barely reached a few tens of kilograms before the German collapse, but its existence confirmed that scientific research had evolved towards increasingly sophisticated compounds. Despite having a significant arsenal, the Reich did not use nerve agents on the European front. Various factors influenced this decision. On one hand, the meteorological risks made dispersion uncertain. A change in wind direction could reverse the effect against their own forces. On the other hand, German intelligence mistakenly assumed that the Allies were aware of the nerve agents and were prepared to produce them on a large scale. The fear of massive retaliation acted as a decisive barrier. The wide Allied air superiority meant that any German chemical attack would be responded to by equivalent or superior bombings on Reich urban centers. The use of these compounds, far from stabilizing the German military situation, could precipitate an even more unfavorable scenario. Therefore, although the weapons were ready for use, they remained in storage until the end of the conflict. Simultaneously with the chemical development, there were biological research investigations. The German authorities evaluated the possibility of using bacteria, such as anthrax or plague, to contaminate water reservoirs or selectively affect enemy troops. Studies on bacterial cultures and dispersion methods in isolated facilities were developed. The obtaining of biological samples and experimentation with microorganisms were carried out under the supervision of doctors linked to the SS, who documented the results in detail. However, the advances were limited. The difficulties in ensuring stability, controlling the spread, and avoiding indiscriminate effects stalled the efforts. The potential for a biological agent to escape control and affect both their own forces and Reich civilians contradicted the immediate tactical objectives. Furthermore, the fluctuating conditions on the European front made it difficult to maintain quarantine zones or manage induced outbreaks. As a result, biological weapons remained in preliminary stages without reaching the operational development level of nerve agents. German nuclear research represented the most ambitious endeavor within the Reich's extreme sciences. The program, known as Uran Project, began formally at the end of 1939, shortly after Otto Hahn and Fritz Strassmann identified fission products by bombarding uranium with neutrons. The interpretation of these results, carried out by Lise Meitner and Otto Frisch, established the theoretical foundations for the development of a self-sustaining chain reaction. At that time, the German scientific community had advanced knowledge in theoretical physics, nuclear chemistry, and radiochemistry, which gave the country a significant initial advantage. Werner Heisenberg, one of the most outstanding physicists of the period, was appointed to lead the research. In December of 1939, he presented an analysis describing the basic operation of a nuclear reactor capable of producing energy and fissile materials applicable to weapon production. The German project initially adopted heavy water as a neutron moderator. This approach was partly due to calculations that ruled out the use of graphite, although it would later be shown that these calculations contained errors that led to an incorrect technical decision. To support the project, Germany relied on the heavy water plant located in Vemork, Norway, under German control since 1940. The strategic importance of Vemork was quickly recognized by the Allies. Between 1942 and 1944, a series of combined commando operations and bombings repeatedly disrupted the production of heavy water. The destruction of the facilities, along with the sinking of a ferry carrying the last available shipment, drastically reduced the supply needed for the German experiments. The lack of this resource, together with the dispersion of the scientific effort in different institutions and the internal competition for resources, prevented the Uran project from reaching operational goals. Although reactor prototypes were built and experiments were carried out in various German cities, none achieved a self-sustaining reaction. The scientists moved their equipment to Haigerloch in 1944 to continue the work in a safer environment, but the lack of critical materials limited the advances. The Allied authorities considered throughout much of the war that the German nuclear development represented a potential threat. The ALSOS project, an integral part of the American Atomic Research Program, was dedicated to assessing German progress and capturing documentation, materials, and scientific personnel. As Allied troops advanced in Europe, reactor components, uranium reserves, and technical files were seized. After the German surrender, the main scientists involved were detained and transferred to the United Kingdom for detailed interrogations. The records obtained demonstrated that Germany was far from achieving a nuclear weapon, although it had accumulated knowledge that could have propelled later developments if the war had been prolonged. The analysis of the German chemical, biological, and nuclear arsenals showed that, although none were used against the Allies, all generated significant concern. The destructive potential of nerve agents, the possibility of uncontrolled bacteriological outbreaks, and the risk of an emerging nuclear capability demanded the creation of intelligence units and specialized technical groups aimed at identifying, neutralizing, and studying each German advancement. The combination of cutting-edge scientific research and a regime willing to employ extreme methods shaped planning scenarios that considered consequences of enormous scale. However, material limitations, technical errors, and Allied military pressure prevented these weapons from reaching a wide operational deployment phase. As the Reich approached its collapse, the scientific projects were scattered at different levels of development, anticipating technologies that would continue to evolve in the months following the end of the conflict: steel twilight, the fall among relics, and extreme prototypes. In the first months of 1944, the Luftwaffe faced a structural degradation that could no longer be reversed through tactical reorganization or limited production increases. The Allied air offensives had reached a scale that surpassed any precedent. Formations composed of hundreds of bombers, escorted by an even greater number of fighters, crossed German airspace daily. The Reich's air defense was reduced to brief and increasingly ineffective interventions, carried out by conventional fighters, suffering both from a fuel shortage and a reduction of experienced pilots. The available aircraft, mostly late versions of the Bf-109 and the Fw-190, could barely approach the bombers before exhausting the fuel needed to return to their bases. Under these conditions, the pressure to introduce weapons capable of locally altering the operational situation increased drastically. The response came in the form of two aircraft that represented a break with all previous aviation: the rocket fighter Messerschmitt, Me-163 Comet, and the jet fighter Messerschmitt Me-262. Both were extraordinary technological advances, but they were introduced in a context where the German infrastructure could no longer support the systematic exploitation of radical innovations. The Me-163 was the first fully rocket-powered fighter that reached operational status in combat. Its design prioritized vertical ascent and extreme speed, providing the aircraft with acceleration capable of taking it to operational altitudes in less than 2 minutes. During tests, the Comet reached speeds exceeding 900 km per hour and climb rates surpassing 3,500 meters per minute, figures impossible for piston fighters available in 1944. The Walter engine, which provided its power, used two highly reactive hypergolic propellants. Concentrated hydrogen peroxide, known as T-Stoff, acted as an oxidizer, while the hydrazine and methanol mixture, called C-Stoff, functioned as fuel. Accidental contact between the two produced violent thermal reactions capable of destroying the aircraft in seconds. Handling required specialized equipment and protective suits due to the possibility of leaks or spills. The complexity of this system made the Comet as dangerous a weapon for its operator as for the enemy it intended to intercept. The structure of the airplane had other limitations. To reduce weight, the Me-163 lacked a conventional landing gear. It took off on a wheeled cart that detached after the initial acceleration. Any failure in that detachment caused damage to the fuselage or explosions resulting from the impact with the propellant tanks. Landing was done on a retractable skid, which required perfectly level surfaces. In real conditions, these maneuvers proved difficult and increased the risk of accidents. The engine's range varied between 5 and 6 minutes, after which the plane became a glider with no capacity for new approaches. Speed was its main advantage and its greatest disadvantage. Pilots had only seconds to align with an enemy bomber, aim and fire before overtaking the target. The Mk-108 cannons, although powerful, had low cadence and relatively slow projectiles, which complicated frontal shots at such high speeds. The unit assigned to the Me-163, the Jagdgeschwader 400, began operations in the summer of 1944. Its first sorties demonstrated that the extreme performance of the Comet did not automatically translate into tactical effectiveness. The brief attack intervals, the difficulty of calculating firing trajectories at near transonic speeds, and the inherent risks of engine operation resulted in limited outcomes. Operational figures collected after the war indicate that the Comet shot down between 9 and 16 Allied planes, while its own losses, between accidents and enemy fire, exceeded 20. Of the several hundred aircraft built, only a minority participated in combat missions. Although it represented an extraordinary innovation from a technical standpoint, the Comet did not achieve strategic impact and ended up symbolizing the practical limits of extreme engineering applied under conditions of military and industrial collapse. The Messerschmitt Me 262 featured a more balanced approach between innovation and operability. Its Junkers Jumo 004 turbojet engines allowed speeds that comfortably surpassed those of the Allied fighters, being around 870 km per hour. This performance allowed rapid approaches against bomber formations that could neither evade nor maintain speed to prevent the attack. The aircraft was equipped with 4 Mk108 cannons mounted in the forward section and, in some variants, R4M air-to-air rockets that offered the possibility of attacking from greater distances and dispersing impacts in compact formations. From a technical perspective, the Me 262 represented the first fully functional jet fighter used in combat. However, its operation was constrained by the fragility of the engines, whose service life was just a few tens of flight hours due to the shortage of heat-resistant metals. The engines required progressive acceleration. Any abrupt increase in power could cause internal compressions, leading to catastrophic failures. Production and deployment decisions were influenced by political interventions that temporarily diverted the airplane's original purpose. Hitler insisted that the Me 262 be turned into a fast bomber, which delayed its introduction as an interceptor fighter. When its use in air-to-air combat was finally authorized, industrial availability was already severely deteriorated. Factories producing engines and components were repeatedly bombed. To avoid total destruction, production was dispersed into underground facilities, improvised workshops, and hidden sections of existing factories. Final assemblies were carried out in remote areas, with components transported by trucks, wagons, and bicycles, which added a significant logistical burden and limited the pace of production. In February of 1945, Adolf Galland received authorization to organize a specialized unit equipped exclusively with Me 262. The Jagdverband 44 brought together some of the most experienced pilots of the Luftwaffe. The presence of veterans with hundreds of kills provided the unit with a considerable level of expertise. However, even under these conditions, the operations of JV-44 faced inevitable restrictions. The German runways were deteriorated or under constant Allied observation. The takeoff phase constituted the moment of greatest vulnerability for the Me 262. To mitigate this risk, Galland organized a protection section composed of FW-190 with high visibility markings, tasked with keeping Allied fighters away while the jet aircraft accelerated. Despite these measures, the engines took too long to reach sufficient power, which exposed the pilots on each mission. During March and April of 1945, the Me 262 achieved localized tactical impacts. In one of the most significant sorties, a group of 37 planes attacked a formation of American bombers, shooting down 12 aircraft. However, although the ratio of own losses to enemy losses was favorable, the scale of the operation was insufficient to modify the overall course of the conflict. Allied losses could be replaced in days, while German production could no longer replenish either planes or pilots with the required speed. The JV-44 continued operations for a few additional weeks, but in a context of continuous withdrawal. Galland was shot down at the end of April, and the unit dispersed in the face of the American advance. Many of the Me 262s that had not been destroyed in combat were set on fire by their own crews to prevent their capture. The deliberate destruction of technological infrastructure was a constant directive during the last few weeks of the Reich. As Allied forces advanced over German territory, efforts intensified to prevent airplanes, missiles, and technical documentation from falling intact into enemy hands. Underground factories, assembly tunnels, and component depots were demolished using explosive charges. Some of the documentation was burned, although a significant number of blueprints, reports, and prototypes managed to survive. Some scientific teams decided to hide information in abandoned mines or bury it in metal containers before surrendering to Allied forces. These actions coincided with the growing interest of the United States and the Soviet Union in obtaining technology and specialized personnel. The process of capturing and transferring German scientists became one of the most significant episodes at the end of the conflict. The United States initiated systematic operations aimed at locating, identifying, and relocating engineers and technicians linked to rocketry, aeronautics, advanced chemistry, and electronics. In the face of the collapse of the Reich, numerous scientists considered that their collaboration with the Allies represented the best opportunity to avoid reprisals and ensure professional continuity. Werner von Braun and part of the team responsible for the development of the V2 moved to areas controlled by the United States in the first days of May of 1945. They had hidden documentation in a salt mine and took essential technical information with them. The formal structure of this process was established under Operation Paperclip, whose purpose was to incorporate German specialists into American scientific programs. Between 1945 and the subsequent years, hundreds of scientists were first moved to evaluation centers and later to facilities defined as Fort Bliss, White Sands, and Redstone Arsenal. Their expertise in liquid fuel rockets, ballistic control, and advanced engine design was considered essential for developing missiles and later spacecraft. The American authorities omitted information related to some of these scientists' involvement in programs that had used slave labor, prioritizing the acquisition of strategic advantages during the post-war period. The Soviet Union implemented similar strategies through operations aimed at transferring machinery, prototypes, nuclear materials, and scientists to Soviet territory. In some cases, entire facilities were dismantled piece by piece and rebuilt in the USSR. The capture of uranium, heavy water, and technical documentation from the German nuclear program provided the Soviets with access to information that complemented their own projects. Although the treatment given to the German specialists differed from that received by those who worked for the United States, the information obtained directly influenced the nuclear and missile race undertaken during the following decade. The legacy of the German prototypes transcended the immediate outcome of the war. The Me-262 provided fundamental information for the development of post-war jet aircraft. The research linked to rocket engines fueled progress in ballistic missiles that would become the foundation of strategic arsenals during the Cold War. The knowledge acquired by von Braun's team resulted in space programs that culminated in placing satellites and sending manned missions beyond Earth's orbit. In this regard, the capture of German technology represented an unprecedented transfer of knowledge. The consequences manifested not only in the development of weaponry, but also in scientific and engineering advances that shaped the second half of the 20th century. As the Reich disintegrated, its operational prototypes ceased to be combat tools and became objects of study. The fighters that had chased Allied bombers in the European skies were transformed into pieces analyzed by American and Soviet engineers. With each captured documentation, each recovered engine, and each scientist relocated, a new scenario was configured in which German technology ceased to be an immediate threat to become a foundational element of projects that would continue to expand in the months following the end of the war.